Partial fractions is the topic of the day. Now we have discussed about fractions in various chapters. Like if I have the fractions like 1 by 2 and say 1 by 3, then what do we mean by partial fractions? In general, we have its own definition. But before we discuss about partial fractions, let's introduce the concept of numbers and understand partial fractions through those example problems. Now, as I see, these are all called the fractions because they are expressed in numerator by denominator form. And then partial fractions also deals similarly in this manner, including the polynomials. That is, if I have a polynomial f of x divided by a polynomial g of x such that g of x is not equal to 0, then I say this is a fraction expressed for the two polynomials where the numerator polynomial is f of x and the denominator polynomial is g of x. Now, the definition of partial fractions comes into existence here in the way that partial, the word partial is nothing but splitting of the fraction. So, if I can split this fraction, that is nothing but the partial fraction. So, in order to obtain the partial fraction of this, I split this fraction using various properties. And the various properties I use in splitting the fractions, the different types of partial fractions expressed in polynomials, is what we are going to study in this topic. So, different fractions have different methods of splitting, the rules which we are going to study in partial fractions. So, basically, partial fractions is nothing but splitting of a fraction gives us the partial fraction of the given fraction. So we define in general the splitting of a fraction as the partial fraction, that is the outcome of after splitting the fraction is nothing but the partial fraction of the given fraction. Say for example, if I have the numbers 4 plus 6 by 2, or I have this and I want to split this fraction, then I just write this as 4 by 2 plus 6 by 2. That means I split this fraction independently by taking the help of the denominator, which is 2. Therefore, this can be written as 4 by 2 plus 6 by 2, which on simplification gives 2 1s, 2 2s, 2 1s, 2 3s, which is nothing but 2 plus 3, which is 5. Therefore, 4 plus 6 by 2 is simplified into the form to give the value 5. So this is how, though it is for the numbers, we try to use the similar methods of splitting the fractions for the polynomial divided by another polynomial, where we split and hence we get the partial fraction with various fractions obtaining various partial fractions. Now that we have discussed about the introduction of partial fractions and its definition, let's introduce the topic types of fractions. So before we understand the splitting of a fraction into the various different terms, we need to understand the various possible fractions which we have in the branch of mathematics. Therefore, in the types of fractions, the first fractions which we're going to deal with is called rational fraction. So the first type of fraction which we're going to deal is called the rational fraction, and let's see how the definition says. So rational fraction is a fraction which can be expressed in the form f of x by g of x, where f of x and g of x are polynomials such that g of x is a non-zero polynomial. So this kind of expressing a fraction where the numerator and denominator are polynomials is called a rational fraction. Is how we define the rational fraction. So for example, if I take 1 minus 2x by x squared plus 2x plus 4. This is a partial fraction because my numerator is a polynomial and my denominator also is a polynomial. This is also a polynomial because this is a constant polynomial and this is a polynomial of degree 2, and therefore this also is an example of a rational fraction. Now this is also a rational fraction, but it is purely a rational number, but I can call this as a rational fraction because it satisfies that it's a constant polynomial divided by a constant polynomial. And it is because the numerator is a polynomial of degree 9 and the denominator is a constant polynomial. So these two are rational, and then if I have 4x minus 1 by 0x squared minus 0x plus 0. Now the reason being that this is not a rational fraction because if I have this denominator, I have that when I simplify this is clearly 0 times 0 times 0. When I simplify, I get 0, where the denominator is g of x equal to 0, which contradicts the definition which says that for rational fraction, g of x or the denominator polynomial must be non-zero polynomial, and hence this cannot be a rational function. This is how we understand the rational functions and its properties. Now, it is very important to note that here, in this case, a rational fraction is also called a polynomial fraction. So, a rational fraction is also called a polynomial fraction, or simply I call this as a fraction, is how I understand the note. The other name for rational fraction is a polynomial fraction or simply a fraction. Now the second type of fraction which we're going to deal is the proper fraction. So that we have discussed about the rational fraction. Now we are going to discuss on the proper fraction in mathematics. Now, what is a proper fraction? How do we define that is the biggest question here. So when I take a polynomial in the form f of x by g of x such that g of x is not equal to 0, then this kind of a polynomial is called a proper fraction is if degree of f of x is less than degree of the function g of x. Now this is the property which defines the condition for a rational fraction reducing to a proper fraction. So the strict condition out here for a proper fraction is that the fraction with numerator by denominator should be in such a case where the degree of the numerator is less than always degree of the denominator. So that is how we understand the proper fraction. Say for example, I have 2x plus 1 by 3x squared minus 4x plus 2. Now in this case, my f of x is the numerator this and my g of x is the denominator, which is the whole polynomial this. Now my degree of f of x, which is nothing but degree of 2x plus 1 is nothing but 1, because we all know that degree of this function is 1. And secondly, my degree of g of x, that is the denominator function, is 3x squared minus 4x plus 2, which is nothing but the highest degree is 2. Now clearly I see that in this case my degree of f of x, which is 1, is less than degree of g of x, which is 2, because 1 is less than 2. Therefore the given polynomial 2x plus 1 by 3x squared minus 4x plus 2 is a proper fraction. Is a proper fraction is how we understand the proper fractions in the branch of mathematics. Now the third type of fraction which we're going to deal is the improper fraction. So what is an improper fraction? It's very simple that the one which is not a proper fraction is an improper fraction. That is, if I have a function f of x by g of x with g of x not equal to 0, then this is called an improper fraction if degree of f of x is greater than or equal to degree of g of x. So under these conditions we call the given function as improper fraction. So it is contradictory to the previous definition which says degree of f of x is less than degree of g of x, but in this case degree of f of x must be greater than or equal to degree of g of x. Say for example 2x cubed by 1 plus 2x. Now in this case my degree of the numerator is 3 and my degree of the denominator is 1, which gives me degree of this is greater than this. Therefore the numerator is greater than degree of the denominator. Therefore I can say from this is an improper function. Therefore 2x cubed by 1 plus 2x is an improper fraction. Is how we understand the three types of fractions: the rational fraction, the proper fraction, and the improper fraction in their own respective definitions and live examples. Now the next concept is the irreducible polynomial. The word irreduce itself defines the whole of the polynomial, irreducible polynomial. The word irreducible implies the one which cannot be reduced. The opposite, the antonym of reducible, is irreducible. So that polynomial which cannot be reduced further is defined as an irreducible polynomial. More mathematically, the definition says that a polynomial which cannot be expressed as a product of a polynomial which cannot be expressed as a product of the other polynomials is called irreducible polynomial. But it is very important to note that the other polynomials here must be always degree less than. Note, if f of x is not able to be expressed as some g of x into h of x, that implies the condition of degree of g of x or degree of h of x should always be less than of degree of f of x. And of course, the constant polynomials are always neglected because any polynomial can be multiplied with 1. So except the polynomial multiplied with 1, I consider those polynomials to be irreducible, which cannot be expressed as a product of the other polynomials, where I can include here saying excluding 1, because 1 is a common factor for every polynomial. So this is how we define the irreducible polynomial. So let's see some examples on what we understand through this irreducible polynomial. For example, I take two x squared plus 1, then this cannot be further expressed as product of real coefficients, but can be expressed in complex. But for a polynomial, this cannot be further reduced. So this is an example of irreducible polynomial. But though this can be multiplied with 1, and then every polynomial can be multiplied with 1 or expressed as a product of two different polynomials, one being a constant polynomial, is a restriction because I exclude 1 in the definition. Therefore, this is an irreducible polynomial. But when I take the polynomial x squared minus 5x plus 6, which can be expressed further as product of two different polynomials, x minus 2 into x minus 3, is not an irreducible polynomial, because this can be expressed as the product of two other polynomials, which gives us the contradiction for the definition. Therefore, this is not an irreducible polynomial. This is an irreducible polynomial. Is how we understand the concept of irreducible polynomials. So it's a very important note I make after we define the irreducible polynomial, that what is a polynomial which is not irreducible called is what we're going to discuss in the note. A polynomial which is not irreducible is called a reducible polynomial, is how we understand. For example, if I take the polynomial x squared minus 4, I can write this as x plus 2 into x minus 2. Therefore, this is a reducible polynomial. But when I take the example x squared plus 4 is not a reducible polynomial, because this cannot be expressed as the product of two different factors. Though I can write this as x squared plus 4 times 1, which contradicts excluding 1, and hence this is reducible, this is irreducible, is how we understand the reducible polynomials and irreducible polynomials. So now that we have defined the reducible and irreducible polynomials, we will try to define the properties involved with reducible and irreducible polynomials with their respective definitions. So with the properties, the first property is that every linear polynomial is irreducible. That is, every linear polynomial cannot be reduced further to the factors because the linear polynomial itself is with degree 1. That is, for example, when I take 2x plus 1, this being with degree 1 cannot be further expressed as factors. This itself is the factor for itself. Therefore, this cannot be reducible. Any linear polynomial taken out there cannot be reducible. So this is an example of irreducible polynomial. This is how we understand. So this is a common property which applies for any linear polynomial where every linear polynomial is irreducible. Now secondly, I have the property which says that if I have, say, x squared minus 9, then if I have x squared plus 9, then I say that this is irreducible. But if I write this as x plus 3i into x minus 3i with I squared equals minus 1, then this is reducible to the product of two different complex polynomials. But polynomial defines that its coefficients must be real. But though this can be expressed as this, still x squared plus 9 is not reducible because these are complex. Complex numbers. The condition for a polynomial to be reduced to the product of two different polynomials is that those two factors as respective polynomials must also have the real coefficients. But because here there are complex coefficients, it fails. Though this can be expressed as product of two different factors, but not polynomials. These two are not polynomials. Now next we have, if suppose I have the polynomial ax squared plus bx plus c is irreducible if it cannot have factors. Very simple that this can be reducible if it can be expressed as product of two factors, but this quadratic polynomial ax squared plus bx plus c is irreducible if it doesn't have real roots. If delta is less than 0 is how we connect irreducibility with discriminant delta. That is, we know that delta is b squared minus 4ac is less than 0. So this is the condition through which we try to connect irreducibility with the nature of roots. Delta less than 0, the roots are real, complex and imaginary. Complex or imaginary. Now let's take an example where I have x squared minus x plus 1. In this case, I have my a equal to 1, b equal to minus 1, and my c equal to 1. So for this quadratic equation, x squared minus x plus 1, let's see if this is reducible or irreducible using the discriminant. Now, as I consider delta, which is b squared minus 4ac, that is b squared minus 4ac, I clearly see this to be 1 minus 4, which is minus 3 less than 0. Therefore, delta less than 0 implies this is irreducible. That implies this is irreducible. Is how we understand the concept of irreducibility of a quadratic function or a polynomial using the discriminant delta. So now that we have discussed about reducible and irreducible polynomials, we have some limitations which we consider here. That is, if my function f of x is reducible to the form g of x into h of x, then the condition is that each of degree of g of x and degree of h of x must be greater than 1, is how greater than or equal to 1 at the most, but cannot be with degree 0. So let's take here, for example, 2x plus 4. Then in this case, I can reduce this into 2 times of x plus 2, but still this is an irreducible polynomial because I want each of them to be with greater than or equal to 0. But since degree of this is 0 and degree of this is 1, therefore I still have each of them must be with greater than or equal to 1. I say that this is irreducible. I still say, though it can be expressed as product of 2 factors, it is still irreducible. Is how we understand. So in this case, with the outcome, we understand that for a polynomial, if a polynomial is reducible, then each of its factors, that is g of x, h of x, or any other third, fourth factors, then each of its factors must have its degree greater than or equal to 1. Is how we understand the limitations of reducible and irreducible polynomials, where though this can be reduced further into 2 times of x plus 2, this is not said to be reducible because the reducibility and irreducibility are based on degree, each of the factors with degree greater than or equal to 1. Now this is with degree 0, which is not greater than or equal to 1. Hence, the given polynomial 2x plus 4 is irreducible, is how we understand the limitations. Cut. Division algorithm. Now we have discussed division algorithm in many of the topics in the previous session. Now let's recap with division algorithm for polynomials. So division algorithm for polynomials is when I generally denote the function f of x and I divide the function f of x with the function g of x with the condition g of x is not equal to 0, then that implies for the polynomials f of x and g of x, there exists q of x and r of x. That is, there exists the other two polynomials q of x and r of x such that f of x is equal to q of x g of x plus r of x. So this relation is always true when I divide f of x by g of x, provided this is non-zero. So under this condition, we call this as division algorithm. F of x is q of x, g of x plus r of x, where either r of x equal to 0, where either degree of r of x, where r of x is 0, or degree of r of x is less than degree of g of x is what is the condition. Either the remainder is 0 or degree of the remainder polynomial is less than degree of the polynomial in the denominator. So this is called the division algorithm. And note, q of x is called the quotient and r of x is called the remainder. F of x, the numerator, is called the divisor, and g of x is called the dividend is how we connect each of f, g, q and r. Division algorithm for polynomials is defined for this. Now let's define a partial fraction. What is a partial fraction? Now that we have defined the proper, improper, rational fractions and reducible polynomials and irreducible polynomials, let's see how partial fractions are defined using the proper fraction and reducible concept. So connecting the reducibility and irreducibility and the proper and improper fractions, the partial fraction is defined in this manner. If a proper fraction can be expressed as a sum of two or more than two proper fractions, then that sum is called the partial fraction. Then that sum is called the partial fraction of the given fraction is how we define the proper fraction. And here it is very important to note that the denominators of partial fraction are powers of irreducible polynomials. That is, you cannot reduce further. They have powers are powers of irreducible polynomials. This is the condition attached to the definition, because though the definition is complete till here, this is very important, which completely defines the partial fraction. Now let's revisit the definition, which says if a proper fraction can be expressed as a sum of two or more proper fractions, then that sum is called partial fraction. That is, if I give a fraction and I want to split that into sum or difference of two different fractions such that the two or more different fractions which are split are also proper fractions, then expressing the given proper fraction as sum of two is called the partial fraction of the given fraction. Now the condition is that we had to express the sum in such a way that denominator of the partial fractions are powers of irreducible polynomials. So let's see this live with more example problems so that we understand this concept more better through the example problem. Now let's take an example problem where we try to understand the partial fractions more better. So for example, I have a problem where I need to split this into partial fractions, that is 2x minus 1 by x squared minus x. Say I have this problem which I want to express as the sum of two proper fractions, that is, I want to express this as partial fractions. Then clearly I see the numerator and the denominator, which are both the proper fractions. Now when these two are proper fractions, then I can clearly take this as x plus x minus 1. By taking x common, I get x times x minus 1. So the same equation can be written in this form, so that when I split as the sum, I get x by x times x minus 1 plus x minus 1 by x times x minus 1. So assuming x is not equal to 0, I get this and this cancelled with x not equal to 1, and I get this as 1 by x minus 1 plus 1 by x. Therefore, the given equation 2x minus 1 by x squared minus x can be written indirectly as the sum of two proper fractions, that is 1 by x minus 1 plus 1 by x, which is called the partial fraction, because this is expressed as sum of for the given fraction. The right hand side is called the partial fraction of the LHS. So the right hand side is called the partial fraction of the left hand side, because this can be expressed as sum of two proper fractions, where the denominators are irreducible polynomials of power 1 each. Is how we understand the partial fractions which are split off the given fraction as sum or difference. So now that we have understood the partial fractions which can be split using the proper fractions, given proper fractions, into the sum or the difference, now we will see the methods of resolving into partial fractions, because every proper fraction cannot be easily split into the sum. It is a difficult task where we use different rules for different types of proper fractions, where we need to resolve into partial fractions for that particular proper fraction. So to start with rule 1, I first initially take the rule 1, in which I take the proper fraction f of x by g of x. Let this be a proper fraction, such that of course g of x is not equal to 0. So for this proper fraction, if ax plus b is a factor of g of x, or it is a non-repeated factor of g of x, the condition is it is a non-repeated, it is a unique factor where it is not repeated twice, where in some case the roots are repeated roots. So if ax plus b is a factor of g of x which is non-repeated, then I can write the given partial fraction. Then partial fraction has one of its term as a by ax plus b. For the number of factors, the number of terms which can be split is in the form of a by ax plus b, where a is a non-zero real number, where a is a non-zero real number. So this is the concept through which I find a. Ultimately, it is about determining a and substituting there. So therefore, there's an important note I make here which says that ultimately the rule 1 is based on finding a. So here the main aim of rule 1 is to determine the value of a. So let's see how we can determine the value of a, which gives us indirectly the partial fraction of the given proper fraction. So to continue with an example problem. So let's take an example problem for the rule 1 which we have discussed in the session. So if my problem is to resolve the proper fraction, say 5x plus 1 by x plus 2 times x minus 1 into partial fractions, then let's see how we can resolve this into partial fractions, that is splitting as the sum or the difference of two or more than. Now as I clearly see that my given proper fraction is 5x plus 1 by x plus 2 times x minus 1. Now, if I see this clearly, my g of x is x plus 2 times x minus 1 and my f of x is 5x plus 1, and the rule 1 says that whatever are the possible factors of gx, then I take the possible factors of g of x are x plus 2 and x minus 1. Therefore, each of the factor can be expressed as in the form a by x plus 2, and this being the other factor x minus 1 can be expressed as some constant, say b by x minus 1. If there's a third factor, then I get plus c by the third factor, and the fourth factor plus d by fourth factor. So number of factors will be number of constants. Of course, the factors must be non-repeated is the biggest condition there. So for this non-repeated, I can write in this form by rule 1. The rule 1 which says about splitting through partial fractions in the form a by x plus 2 plus b by x minus 1. Now next is to find a and b. The next concept is to find the values of a and b. So let's see how we can find a and b for this particular problem, proper fraction. Now as I take on the left hand side, this is 5x plus 1 by x plus 2 times x minus 1, which on the right hand side, when I take the LCM, now here I get the factors as x plus 2 times x minus 1, where when the LCM is x plus 2 times x minus 1, then this is a times of x minus 1 plus b times of x plus 2 is what we get when I take the LCM of these two terms. Now, assuming that x is not equal to 1 and x is not equal to minus 2, as from the given problem, this and this get cancelled, and finally I have this equal to this. So therefore, continued from the previous session, I have my 5x plus 1, which can be written as a times x minus 1 plus b times x plus 2. So from this equation, I find the values of a and b and substitute in the original partial fraction. So therefore, initially, if I want to eliminate a, I take x equal to minus 2, and to eliminate b, I take x equal to 1, minus 2. So let me take first x as minus 2 and see what happens. So x equal to minus 2 in this equation implies 5 times of minus 2 plus 1 is a times minus 2 minus 1 plus b times minus 2 plus 2. Therefore, x equals minus 2 implies this, substituted in equation 1. Now this and this get cancelled. Therefore, this reduces to minus 10 plus 1 is minus 3a plus 0, because b times of 0 is 0. So that I get minus 3a equals minus 9, because minus 10 plus 1 is this. That implies a equals 3. So I got the value of a equal to 3 by substituting with a fixed value x equal to minus 2. And the substitution of the values of x depends on either I eliminate a or b. Now because I wanted to eliminate b, I want to take this minus 2 so that this reduces to 0. Now next, my target is to eliminate a. Therefore, clearly I understand that I substitute x equal to 1, then I get 1 minus 1 as 0, thus eliminating a. So therefore, x equal to 1 implies 5 times of 1 plus 1 is a times 1 minus 1 plus b times 1 plus 2. Thus, this gets cancelled and I get this as 5 plus 1, which is 6, is 0 plus 3b. That implies a is 3b, and that implies my b is equal to 2 on further simplification. So therefore, b is equal to 2 implies I get a equal to 3 and b equal to 2 implies when substituted in the original partial fraction, I get, therefore a is equal to 3 and b is equal to 2 implies the partial fraction 5x plus 1 by x minus 1 into x plus 2 can be written as 3 by x minus 1 plus 2 by x plus 2 is how I get the partial fraction of the given problem. So this is called the partial fraction of the given proper fraction, and totally depends on finding the values of a and b from rule 1 of resolving into partial fractions. Now next see the rule 2 of resolving into partial fractions for the given proper fraction. Now say I have the proper fraction f of x by g of x, where my denominator polynomial g of x has repeated and or non-repeated linear factors. So on a case that g of x has repeated and or non-repeated linear factors comes under rule 2. Rule 1 is about not having repeated roots. That is, if g of x has non-repeated roots only, it comes under rule 1, and g of x has repeated and non-repeated or only repeated roots. In that case, we have this case coming under rule 2. So for this, the denominator is identified for those repeated roots, and see how this can be split into partial fractions using the rule 2. So if g of x, say for example, if g of x has n repeated factors, ax plus b, so on and so forth till n times, then for these n repeated factors which are all same for g of x, I can split this using a1 by ax plus b plus a2 by ax plus b whole square plus a3 by ax plus b whole cube till an by ax plus b whole power n is how I understand splitting of n same factors, with each time the power increasing by 1, 2, 3, 4 till n. So now the aim is to determine a1, a2, a3 and an. So therefore here I get this with an important note that the aim of rule 2 is to identify the repeated factors and determine the values of a1, a2, a3 till an is how I understand the rule 2 of the resolving into partial fractions. So let's see one problem where I have repeated factors, repeated linear factors, and I split this into partial fractions. Now let's take an example problem to understand the rule 2 more better. But in case of this example problem, I try to take the combination of both rule 1 and rule 2 so that the students understand the application of partial fractions to the best they can. So if I take a problem where I have the question which says resolve the proper fraction x square plus 13x plus 15 by 2x plus 3 into x plus 3 whole square. Then resolve this. Let's see how we can resolve this into partial fractions. So initially I see that the given problem is x square plus 13x plus 15 divided by 2x plus 3 times x plus 3 whole square. Now, as I see the denominator, I clearly see that the denominator g of x has one repeated root and one non-repeated root in its linear factors. So this has 2x plus 3, which is a non-repeated linear factor, and x plus 3, which is a repeated, of course here repeating twice, linear factor. So I identify that 2x plus 3 is a non-repeated linear factor and x plus 3, which repeats twice, is a repeated linear factor. Therefore, in case of this, I use rule 1, and in case of this, I use rule 2. It's as simple as applying both rule 1 and rule 2 into the problem. So applying both rule 1 and rule 2, rule 1 for this and rule 2 for this, because it has repeated roots, repeating twice, I have this using the rule which says that for rule 1, I can split according to its linear factor. The non-repeated linear factor is a by. Now, in case of this, where I use rule 2, because it has two repeated roots or linear factors, I can split this as b by the first linear factor raised to 1, and then with this raised to square. And if I have this repeating 3 times, then I even have d by x plus 3 whole cube, so on and so forth till power n, as we have seen in the previous case of rule 2. So with this ends here, and it is now the target to find a, b, and c and substitute in this equation 1. So substituting a, b, c in equation 1, we then get the partial fraction of this proper fraction expressed as sum of this, this, and this. So let's see how we can find a, b, and c. Now proceeding in the similar manner as in the previous problem, I have this which can be written as x squared plus 13x plus 15 by 2x plus 3 into x plus 3 whole square, which can be written as a by this, so that I take the whole of LCM, which is 2x plus 3 times x plus 3 whole square. So LCM of each of these is this, on further simplification, which gives a times x plus 3 whole square plus b times into x plus 3 plus c times of 2x plus 3, so that the denominator gets cancelled and I get this equal to this. So let's see how we can find a, b, and c using the numerator of this equal to numerator of that. So therefore, we get the equation continued from the previous session as x squared plus 13x plus 15, which is a times x plus 3 whole square plus b times 2x plus 3 into x plus 3 plus c times 2x plus 3. Now it is to find the values of a, b, and c. Now, as we have seen in the previous problem, it is not always an easy task to substitute the value of x and then do. Sometimes we need to expand this and equate the like coefficients. So let's do this by the method of equating the like coefficients, where I get this on splitting x squared plus 6x plus 9 using a plus b whole square plus b times 2x squared plus 9x plus 9 plus c times 2x plus 3. Now this, on taking all x terms one side, x terms and constants as we have in the order x squared, x and constants. Similarly, I place them in the order of x squared terms, x terms and constants out here. Therefore, all the x squared terms which are available here, I just take in the form a plus 2b times x squared. So this is the x squared term out in the previous line. Similarly, I take next all the x terms, that is this, this and this, which gives me 6a plus 9b plus 2c times of x is what we get as times of x. Then coming to the constants, 1, 2, 3 gives me 9a plus 9b plus 3c, which comes as the constant. So these are the terms which I get when I split them according to x squared, x and constants. Now the left hand side being x squared plus 13x plus 15. Now as I see that the coefficient of x squared here is 1 and the coefficient of x squared is here, I understand when the two polynomials are equal, their coefficients, their like coefficients are also equal. Using the equality of the polynomials, I have this equal to this and 13 equal to this and 15 equal to this. Therefore, I have equating the like coefficients, I get a plus 2b is 1 and 6a plus 9b plus 2c is 13 and 9a plus 9b plus 3c is 15. Now how do we find a, b and c from these three equations having three unknowns a, b and c? We use the method of solving by simultaneous method. So in case of simultaneous method, I take this as equation 2, 3 and 4 and first solve using the first two equations. So I initially try to eliminate c and then I get an equation in a and b. So to eliminate c, I want to make the c coefficients equal. So 3 times this multiplied with this equation and this multiplied with this equation makes the constants coefficients of c equal. Therefore 3 times of equation 3 minus 2 times of equation 4 gives me 3 times multiplied of this gives me 18a plus 27b plus 6c is 13 3s 39, and the next equation multiplied with 2 gives me 18a plus 18b plus 6c is 30, which on subtraction gives me this and this cancels, and 27b minus 18b, which is 9b, equals minus 9, and hence minus b equals minus 9. This gives me the value of b as plus 9, and therefore my value of b is 1. I get my value of b is equal to 1, and once I get the value of b, I substitute in equation 2. That is, substituting in equation 2, I get a plus 2b equal to 1, where in place of b I substitute the value of 1, so that this gives me a equals 1 minus 2, that is minus 1. So I get a and b. It's very easy to substitute in one of the equations 3 and 4 and get c. Therefore, substituting a and b values in equation 3, I get this to be, substituting, I get the value of c. So now that I got a equals minus 1 and b equal to 1, substituting a equals minus 1 and b equal to 1 in equation 3, I get the value of c. That is, in 3, I get 6a, that is 6 times of minus 1, plus 9b, that is 9 times of b, which is 1, plus 2c equals 13 is what we get when we simplify. That is, this is minus 6 plus 9 plus 2c is 13, which on further simplification gives 2c equals 13 plus 6 minus 9. And this is 19 minus 9, that is 10. So I get c equals 5. Therefore, finally, I substitute a equals minus 1, b equals 1, and c equals 5 in equation 1. I get the whole of the equation reducing to x square plus 13x plus 15 by 2x plus 3 times x plus 3 whole square, which is a by, that is minus 1 by 2x plus 3 plus b by x plus 3. So therefore, I get this as plus 5 by x plus 3 whole square. Therefore, this proper fraction on the left hand side is expressed as the partial fraction of 3 terms, which is obtained from both rule 1 and rule 2 for the second 2 terms, using both the rules. This example problem done for splitting into partial fractions. Now let's see the rule 3 of resolving into partial fractions. Now in this case, we consider the denominator polynomial g of x, which has a non-repeated quadratic irreducible polynomial. That is, if I have a proper fraction f of x by g of x such that my g of x is, if ax squared plus bx plus c is one of the non-repeated irreducible factor of the polynomial g of x, then I can split ax plus b by ax squared plus bx plus c is one of the term in its partial fraction. Then this is one of the partial fraction term of the given proper fraction f of x by g of x. So this clearly makes us understand that the denominator should have one quadratic polynomial which is irreducible and which is non-repeated factor of g of x. Then immediately that quadratic irreducible polynomial can be expressed as ax plus b by this, which stands as one of the partial fraction term of this. So let's see with an example problem to understand this concept more better. So let's take an example problem to understand rule 3 more better. So for example, I have a problem which says resolve the proper fraction 2x squared plus 1 by x cubed minus 1 into partial fractions. So let's see how I can resolve this into partial fractions, initially identifying with the type of factors we have for the denominator g of x. So in this case, my problem is 2x squared plus 1 by x cubed minus 1, which is a proper fraction. Now in this case, I have my g of x, which is x cubed minus 1, and let's see if I can further split this into the factors. So when I express this, I have 2x squared plus 1 by x cubed minus 1 can be written as 2x squared plus 1 by x cubed minus 1, which is a cubed minus b cubed. That is, a cubed minus b cubed is a minus b into a squared plus ab plus b squared is what we get. Now here, the simplified form of the denominator polynomial g of x is this, where one is linear and one is quadratic. So this is linear and this is quadratic, and clearly I see that this is irreducible, because if I want to check for its reducibility or irreducibility, we have discussed that we find the discriminant delta. That is, here delta is b squared minus 4ac, that is b squared minus 4ac, which is minus 3 and less than 0, and hence this is irreducible, is what we get as irreducible, quadratic, non-repeated linear factor. Therefore, I use rule 3 here and rule 1 here, because this is a non-repeated linear factor. So here I get rule 1 and here I get rule 3 applied for solving this or resolving this into partial fractions. Therefore, this reduces to 2x squared plus 1 by x minus 1 into x squared plus x plus 1, which gives me this partial fraction split as a by x minus 1 plus bx plus c by x squared plus x plus 1. Now in this case, I find a, b and c by using the concept of finding a, b, c by LCM method. Now this is rule 1 and this is rule 3, which I applied because this is a quadratic non-repeated linear quadratic non-repeated irreducible polynomial. Therefore this has its form bx plus c by x squared plus x plus 1. This is how we understand this kind of a partial fraction using rule 3, and this we already know is the rule 1. Therefore the combined rule of 1 and 3 gives me this split as a by x minus 1 plus bx plus c by the quadratic x squared plus x plus 1. And now it is our aim to find a, b and c using the method of LCM. Therefore, continued from the previous session, I got this split as partial fractions for the problem 2x squared plus 1 by x cubed minus 1, which was split as 2x squared plus 1 by x minus 1 into x squared plus x plus 1, and this is a by x minus 1 plus bx plus c by x squared plus x plus 1. So this was equation 1, through which I'm going to find the values of a, b and c. So this, on taking LCM, I get this as x minus 1 into x squared plus x plus 1. Being the LCM, the numerator reduces to a times x squared plus x plus 1 plus bx plus c times x minus 1. So that this on the left hand side is 2x squared plus 1 by x minus 1 into x squared plus x plus 1. Now since the denominators are same, they get cancelled, and I get this to be 2x squared plus 1 is a times ax squared, but I want to take all the like coefficients together, so a plus b x squared. So the coefficients of x squares, or a and b, which when combined gives a plus b x squared. Next is all the x terms, which give a plus c minus b, that is a minus b plus c times of x, and the constant is a minus c, which I get as the constant. So therefore, this is where I'm going to solve a, b, and c. So equating the like coefficients, I get this to be equating the like coefficients, I get a plus b equal to 2, and then a minus b plus c equal to 0 because there's no x term. So a minus b plus c is 0, and finally a minus c is equal to 1. So we have to solve these three simultaneous equations where I take first initially this and add them up. That is, I take a minus b plus c equal to 0 and a minus c equal to 1, and I just add them so that I get 2a minus b equals 1. And already I have a plus b equal to 2 from here, which is brought, so that again when I add, I get 3a equal to 3. That implies a equals 1. So one of the value of a is equal to 1. So when a is 1, substituted in here, b gives a plus b, that is 1 plus b equal to 2, implies b is equal to 1. So I got the value of a and b, which substituted in either this equation or this equation gives me the value of c. So I take the equation a minus c, and from this equation a minus c equal to 1 implies a, which is 1, gives me 1 minus c equal to 1, such that this gives me c equals 0. Therefore, with the three values of a, b, and c substituted in equation 1, we get the given proper fraction resolved into partial fractions. Therefore, the values of a equal to 1, b equal to 1, and c equal to 1, when substituted in 1, we get the given problem, that is 2x squared plus 1 by x cubed minus 1, which was expressed as a by x minus 1 plus bx plus c by x squared plus x plus 1, reduces to a, which is 1, that is 1 by x minus 1 plus bx plus c, that is 1 times x plus c, which is 0, by x squared plus x plus 1. So this, on further simplification, gives me 2x squared plus 1 by x cubed minus 1, which can be split as 1 by x minus 1 plus 1 by x squared plus x plus 1 is how I split the given problem into partial fractions. So I get this as x by x squared plus 1. So 1 by x minus 1 plus x by x squared plus x plus 1 are the two partial fractions which we get from the given proper fraction. So this is resolving into partial fractions using rule 3 of the given methods. So now that we have seen the different rules of resolving into partial fractions for a given proper fraction, now let's see how we can understand the whole of the partial fraction process for the combined rules. So if, for example, if I have a problem which is in the form of 1 by x minus 1 whole square, or x minus 1 times 2x plus 3 whole square, and this being x squared minus 1 whole cube. So I have all the three rules combined out here, where this is understood as non-repeated linear factor, that is irreducible polynomial linear factor. This is repeated linear factor, and this is repeated quadratic factor. So I have three different rules out here, this with rule 1, rule 2 and rule 3 of what we have discussed in the previous session. Therefore, applying each of the rules, let's see how I can split this into partial fraction form in order to convert this proper fraction into a partial fraction. The proper fraction into partial fraction can be resolved using all the three rules combined. Let's see how we can do this for this example problem. Now here, this is a linear factor, therefore I have this in the form a by x minus 1. Plus, now this is a repeated factor, so I have the rule 2 which says first the linear factor comes as power 1 and then it comes as 2x plus 3 whole square. So this with rule 1 and this with rule 2, and finally I got to apply rule 3 here because this is a quadratic factor but repeated. So here I get because for quadratic we have the numerator as ax plus b, that is dx plus e by x square minus 1. But because it's repeated, again with applying the similar rule 2 out here, my next term out here would be this, and next comes cube. Is how we understand splitting into partial fractions. Now the task is about finding each of a, b, c, d, e, f, g, h and I using the resolving process as we have seen in the previous cases. So this kind of problem where we include all the three rules is understood in the form of rule 1, rule 2 and finally this with rule 3. So these are the ways through which we resolve into partial fractions. Each of the denominator is examined before we decide on whether we are going to use the rule 1 or rule 2 or rule 3. So remember, denominator plays a vital role in resolving into partial fractions. Is how we understand this concept. Now that we have discussed on resolving the proper fractions into the partial fraction form, what happens if the given fraction is not a proper fraction? That is, if the fraction is an improper fraction, then how do we resolve that into partial fractions is the biggest question raised in the session. So, in case of for improper fraction, we have already discussed that an improper fraction is a fraction in the form f of x by g of x is an improper fraction if degree of g of x is equal to f of x or degree of g of x is less than degree of f of x. That is, in this case, the degree of f of x is greater than degree of g of x or at the most equal, but it's not less. If the degree of f of x is less than degree of g of x, then that fraction becomes a proper fraction. Is how we have discussed the definitions in the previous sessions. So therefore, this being an improper, if this is an improper fraction, that implies degree of f of x will be at the most greater than or equal to degree of g of x. Is how we have with definition of improper fraction leading to this property. So based on this, we decide whether the given fraction is proper or improper, and if it is a proper fraction, we use the first three rules of the previous session in order to convert or resolve into partial fractions. But if the given fraction is improper fraction, then how do we resolve that into partial fractions is the biggest question out here. So in this case, let's see how we can resolve into partial fraction form. So for an improper fraction, there are two possibilities or the two cases where case 1 is my degree of f of x might be equal to degree of g of x, and in this case my degree of f of x is greater than degree of g of x. So in either of the cases the method is the same, where we use division algorithm. So let's see how we apply division algorithm in resolving into partial fractions for a given improper fraction. Is how we're going to discuss in the session continued. Now we use the concept of resolving into partial fractions for improper fraction is based on using of division algorithm. So this is very important that this is solved using division algorithm. Now, what is division algorithm? Division algorithm, as we have discussed in the previous session, states that if a function f of x or a polynomial f of x is divided by another polynomial g of x, assuming g of x is not equal to 0, then there exists, that implies there exists qx and rx such that f of x is g of x times q of x plus r of x. So this is what we're going to use in resolving the given improper fractions into the partial fraction form. So division algorithm, where either r of x is equal to 0 or degree of g of x is less than degree of r of x less than degree of g of x, is how we understand the concept of division algorithm connected with improper fractions. So let's see with an example problem on how we can resolve a given improper fraction, with first case being degree of f of x equal to degree of g of x resolved into partial fractions. Now let's take an example problem and of the case 1 where degree of f of x is equal to degree of g of x. So if I want to resolve this into partial fractions, say the problem being x squared by x minus 1 into x minus 2, then clearly I see that degree of this is 2 and degree of this one multiplied also is 1 plus 1, which is 2. Thus this is case 1 of the given problem, is in under case 1, that is degree of f of x equals degree of g of x. So for this problem, clearly this being an improper fraction of case 1, let's see how I can resolve this into the partial fraction form. So because this is divided with this, now we know that the division process is when I divide this with x squared divided by x minus 1 into x minus 2, that is x squared minus 3x plus 2, because when I multiply this, this reduces to x squared by x squared minus 3x plus 2, which comes out here. Therefore, when I divide this with this, we know that the division process is this multiplied with this gives me x squared, and then minus 3x into 1 is minus 3x, and plus 2 into 1 is 2, so that on subtraction this gets cancelled and I get 3x minus 2. So I get this to be 3x minus 2, and here I cannot further simplify, therefore my quotient is this and my remainder is this. So I can represent this in the quotient and remainder form, because this is my q of x and this is my r of x, this is my f of x, and this is my g of x. Therefore each of f, g, q and r are connected with the division algorithm. Therefore by division algorithm we get f of x is g of x times q of x plus r of x, which, being the division algorithm, when substituted with each of the values of f, g, q and r, reduces to. So to continue, my division algorithm reduces with x squared equals qx, which is 3x minus 2, and g of x, which is x squared minus 3x plus 2 times of 1 plus r of x, which is 3x minus 2. So this is finally something which we obtain using division algorithm. Now, if in order to obtain the original improper fraction, I can just divide this with throughout, with denominator, divide throughout with x minus 1 into x minus 2, which is the denominator g of x of the given fraction. So if I divide this with this, I get x squared by x minus 1 into x minus 2, but this can be factorized as x minus 1 into x minus 2 by x minus 1 into x minus 2 plus 3x minus 2 by x minus 1 times x minus 2. So this clearly gives me the things cancel, and this can be split as x squared by x minus 1 times x minus 2 is 1 plus 3x minus 2 by x minus 1 times x minus 2. So here we need to, in order to just split this or resolve into partial fractions, we get this in the form where this has to be split into the partial fractions and then substituted in this. So let me take this as equation 1 and then resolve this using, because this is a proper fraction, I can resolve this using the first 3 rules. So let's take 3x minus 2 by x minus 1 times x minus 2 and resolve this into partial fraction using rule 1, because clearly these two are non-repeated linear factors. This can be split using a by x minus 1 plus b by x minus 2, which on LCM gives me x minus 1 times x minus 2, that is a times x minus 2 plus b times x minus 1, that is 3x minus 2 by this equals this, which on further simplification gives this denominators cancelled, and I get this to be 3x minus 2 is equal to all x terms I take common as a plus b times x, and this is minus b. Now equating the like coefficients, I get this equals this and this equals this. So therefore, equating the like coefficients, a plus b is 3 and my 2a plus b is 2. Taking minus cancel on both sides, I get 2a plus b is 2. So that when I simplify this 2, bringing this term here, I subtract and I get this cancelled and I get minus a is 1, so that a is minus half. So when a is minus half, that implies my b is 3 minus a, that is 3 minus of minus, that is plus half, 7 by 2. So the value of a is 1 by 2 and the value of b is, therefore value of a is minus 1 by 2, and when substituted here, b equals this, which is 7 by 2. Now we substitute the values of a and b in this equation, and then let me take this as equation 2, and then I get this resolved into partial fractions, which then substituted here gives me the overall partial fraction resolving. Therefore, a is minus half and b is 7 by 2, which I substitute in equation 2, so that I get 3x minus 2 by x minus 1 times x minus 2 is a, which is minus half of x minus 1, plus b, which is 7 by 2 times of x minus 2, which is taken as equation 3. Now I'm going to substitute in place of this the equation 3 in equation 1 so that I get the overall resolved partial fraction. Now substituting 3 in 1, I get, with substitution of equation 3 in equation 1, I get x squared. So therefore I have x squared by x minus 1 into x minus 2 equals 1 minus 1 by 2 times x minus 1 plus 7 by 2 times x minus 2, which is the partial fraction form of the given improper fraction of case 1. Degree f of x equals degree g of x. Now let's see the case 2 where the degree of f of x is greater than degree of g of x in case of an improper fraction. Now with an example problem, if I have x power 4 by x minus 1 into x minus 2, which needs to be resolved into partial fractions, then clearly this is where degree of x power 4, which is the numerator, is 4, and the denominator being degree of x minus 1 times x minus 2 is 2. So this is how we need to split the degree of f of x and degree of g of x. Now clearly I see that degree of the numerator is 4, which is greater than the degree of the denominator, which is 2. So let's see how we can use the case 2 by using division algorithm. It is as similar as case 1 because it is about using the division algorithm and splitting. So going by the similar process as in case of case 1 of the previous problem, let's see how I can divide the two terms. So as this can be split as x squared minus 3x plus 2, when combined through the factors, this can be, initially I need x squared to make this x power 4 using the division of two polynomials. X squared times x squared is x power 4, minus 3x times x squared is minus 3x cubed plus 2x squared. 3x cubed minus 2x squared, where it is in short of x, which I need to multiply here with, of course, 3, which also needs to be multiplied. Then I get x squared times 3x is 3x cubed, and minus 3x plus 3x is minus 9x squared plus 6x, which on simplification gives me 9 minus 2, which is 7x squared minus 6x. Now this on further simplification gives me this needs plus 7, so that 7 times x squared is 7x squared, and minus 3x plus 3x is minus 9x, and then plus 2 plus 7 is 14, and then this gets cancelled, and 9 minus 6 is 3x minus 14. So this is q of x, and this is r of x, and of course f and g are also there. So using the division algorithm, I get this converted by division algorithm. So therefore by division algorithm I have f of x. Here my quotient is this, my remainder is this, my f of x is this, and my g of x is this. Therefore going by division algorithm, which says f of x is g of x times q of x plus r of x, that implies my f of x, which is x power 4, is g of x, which is x minus 1 times x minus 2 when split, times q of x, which is x squared plus 3x plus 7 plus r of x, which is 3x minus 14. That implies when I divide this term here on both sides, I get x power 4 by x minus 1 times x minus 2 is plus 3x minus 14 by x minus 1 times x minus 2, because this term gets cancelled when split, and this being same get cancelled, and finally I get this. This needs to be split using rule 1 of the previous proper fraction concept. So it is as similar as the previous problem where we reduce into partial fractions after dividing the numerator with the denominator using the division process of the polynomials, and once I get Q and R, my division algorithm connects F, G, Q and R, and we substitute and divide the denominator on both sides such that this gets split into partial fractions. This, being a proper fraction, has to be split using rule 1, linear non-repeated factors. This is how we understand this concept. Now, let's see the conversion of the given fraction f of x by g of x in power series of x. Usually, this concept arises when mod x is less than 1. That is, if x lies between -1 and 1, that is, for -1 less than x less than 1, I have generally the power series of 1 by 1 minus x, which can be split as 1 plus x squared plus x cubed till x power k, so on and so forth till infinity. So the expansion of this is this, using the binomial expansion which we have seen in the previous topics of rational index and integral index. Now, similarly, 1 by 1 plus x is 1 minus x plus x squared minus x cubed till infinity. And then I have two more expansions which come out as 1 by 1 minus x whole square, which is taken as 1 plus 2x plus 3x squared plus 4x cubed plus k plus 1 of x power k till infinity. So this is the expansion of 1 minus x whole square in the denominator as 1 by 1 minus x whole square. Similarly, 1 by 1 plus x whole square will have alternate plus and minus of the previous series, that is 1 minus 2x plus 3x cubed minus 3x squared minus 4x cubed. So we get minus 1 whole power k of k plus 1 x power k, so on till infinity. So these are the four basic formulae which we have in expanding the polynomial f of x by g of x in power series of x for mod x less than 1. This, and this is how we connect the partial fraction into power series in x. Now let's see the general form of what happens when I take 1 by 1 minus x whole power n or 1 by 1 plus x whole power n, to be continued in the session. So if I have, say, n belongs to z is an integer, then 1 by 1 minus x whole power n, let's see how this can be split as power series of x in its more general form. So in its general form, let's see how for n belonging to z this can be split. This has its formula with 1 plus nx plus n times n plus 1 by 2 of x, and then n plus 1 n plus 2 by 3 of x squared, and then so on and so forth till infinity is how we get the formula. This is how we get the expansion, where 1 plus nx plus this times of x squared, this times of x cubed, so on and so forth, is how we identify the formula for 1 by 1 minus x whole power n as power series of x. For each n, we substitute on the right, on the respectively for that value of n, and we get this expanded form of this as power series of x. Now let's see how partial fractions is applied for conversion. So this topic is exclusively about solving problems where partial fractions help us in converting the given division fraction into power series of x. So applications of partial fractions in conversion of this into power series of x is what we are going to see in the session. So let's see the application of this in the given concept. Say for example, I take the question which says find the coefficient of x power 4 in the expansion 3x by x minus 2 times x plus 1. So I want to find the coefficient of this in the expansion of this. So in the expansion of this, let's see how we can find the coefficient of x power 4. So in order to expand this in power series form, I split this into partial fractions as 3x by x minus 2 into x plus 1, which can be split as a by x minus 2 plus b by x plus 1 of rule 1, and I get this to be a plus b of x plus a minus 2b by x minus 2 of x plus 1. Therefore, simplifying, I get my a and b as a plus b, which is 3, and a minus 2b, which is 0, because there's no constant. So when a is 2b, then 2b plus b is 3 when substituted in this, and I get b equals 1 and a equals 2. Therefore, 3x by x minus 2 times x plus 1 can be split as a by, that is 2 by x minus 2 plus 1 by x plus 1 is how I get the partial fraction. Now I use this partial fraction form in expanding into the power series form. So let's see how we can expand. Therefore, my given problem 3x by x minus 2 times x plus 1 is split as 2 by x minus 2 plus 1 by x plus 1, which I'm going to convert using the partial fraction form. So here I clearly see that this fraction 2 by x minus 2 can be written as minus 2 taken common and written in this form. So I would like to reduce this into the 4 formulae which are taken, which is in the form 1 by 1 minus x form. So therefore, taking 2 common, and this is directly in the form 1 by 1 plus x. Therefore, this is in the form of minus 1 by 1 minus x by 2 plus 1 by 1 plus x. Now this is 1 by 1 minus x, which is clearly 1 by 1 minus x is 1 plus x plus x squared plus x cubed, so on till x power 4 plus so on until infinity. And this with 1 by 1 plus x is 1 minus x plus x squared minus x cubed plus x power 4 minus so on and so forth. So we get this in the form of expansion where it is 1 minus x plus x squared minus x cubed plus x power 4, so on and so forth. Now in this case of the problem, at this stage it is very important to validate the expansion. So let's see how we can validate the expansion. Validity of the expansion. Now here I have two expansions which we have taken. One is 1 by 1 minus x by 2 and one is 1 by 1 plus x. So in this case, mod x by 2 is less than 1, and in this case mod x is less than 1, or two cases which we have for the second expansion and the first expansion. So therefore mod x by 2 less than 1 implies mod x is less than 2 brought to the right, and mod x less than 1. Therefore this implies minus 1 less than x less than 1. Therefore, for mod x less than 1, both the expansions, therefore for mod x less than 1, both the expansions of 1 by 1 minus x by 2 and 1 by 1 plus x are valid, is how we validate the expansion. And once we validate the expansion, then we expand with this. So if the question refers to validate the expansions, we need to justify through mod x less than 1 or less than k, and then proceed with the expansion. Therefore, for mod x by 2 less than 1 and mod x less than 1, this expansion is valid for each of these cases. Now question comes on how we find the coefficient of x power 4 for these valid expansions in the given intervals of this less than 1 and this less than 1. So coefficient of x power 4 in the expansion of 3x by x minus 2 times x plus 1 is given by the coefficient of x power 4 is minus 1 by 16 clearly out there, and here the coefficient of x power 4 is 1 is what we get. Therefore simplifying this through LCM, I get 16 minus which comes as 15 by 16. Therefore coefficient of x power 4 is 15 over 16. That's how we understand finding the coefficient of x power 4 using the power series expansion and of course through application of partial fractions. Therefore, one of the applications of partial fractions is that any given proper or improper fraction, I can convert that into power series, as can be seen in this case where I split initially using the partial fractions, and once I get the split into partial fractions, only then I can use the power series expansion, and then the respective terms as can be obtained. Coefficients of x power n for any n belonging to z can be obtained using the expansion, is how we understand the applications of partial fractions in conversion of the given fraction polynomial into power series of x through validity of the expansion using mod x less than 1.